Hi everyone, I'm Sooyoung and I'm a PhD student from Korea University. In this talk, I will present my new research making symbolic execution promising by learning aggressive state pruning strategy. This work is co-work with Hakjoo. Before introducing our work, let's start with a brief introduction of symbolic execution and the motivation of this work. Please enjoy my talk. As you know, symbolic execution is a powerful software testing technique. This technique aims to maximize code coverage and find many bugs in a limited time budget. And because of its well-known effectiveness, many symbolic execution tools such as KLEE are actively used both in academia and industry. However, in practice, symbolic execution still suffers from an open challenge, namely the state explosion problem. The problem is that the number of execution states is usually exponential in the number of branches in the program. So exploring all states of any real-world program is simply impossible. That is, when performing a symbolic executor on real-world program, we must face the state explosion problem. And this problem will significantly increase the memory usage of the tool. So in practice, the symbolic executor like KLEE takes the memory budget as an input and maintains as many states as possible within the given memory budget. However, this reasonable solution raises two practical problems. First, preserving as many states as possible within the given memory budget is to naturally increase the total number of candidate states. So symbolic executor can hardly know which states are promising among the older candidates. In our work, we define the promising states as having the potential to effectively increase branch coverage when they are further explored. The second problem is that testing real-world programs easily exceeds the given memory budget. So to reduce the memory usage, numerous states are inevitably pruned. More concretely, when performing KLEE on open source C programs by using the default memory budget 2 GB, we observe that the number of candidate states is more than 10,000 on averages. That is, KLEE should select a promising state among the 10,000s of candidate states, which is a very difficult task. Second, to reduce the memory usage, the number of blindly pruned states ranged from tens of thousands to hundreds of the thousands on averages. That is, we might lose many promising states due to the memory overrun. So in this work, we aim to minimize the total number of candidate states while keeping promising states during symbolic executions. To achieve this, we have to overcome two technical challenges. First, we should be able to evaluate how promising each state is, and we should be able to decide how many candidate states are pruned. To overcome these two challenges, the first key idea is to define the probabilistic state pruning strategy having two distributions. The first distribution is to score how promising each state is. The second one is to decide how many states are pruned. That is, we reduce the problem of solving the two technical challenges into the problem of learning both probabilistic distributions. The second key idea is to present a learning algorithm that continuously updates these two distributions aligned during symbolic executions. In this work, we implemented our tool HOMI on top of KLEE, which is a very popular symbolic execution tool. By the way, have you ever heard the word HOMI? HOMI is a famous gardening tool in South Korea. In our context, HOMI aims to cut the redundant state and find many software bugs in a limited time budget. And HOMI is an open source tool, and this is GitHub URL. This slide briefly shows the effectiveness of HOMI. As you can see, HOMI, this purple line, is able to maintain a really small number of candidate states during symbolic executions. Second, HOMI is also able to significantly increase the branch coverage compared to vanilla KLEE. Lastly, HOMI is able to find program crashes such as abnormal termination and segmentation fault in the open source C programs, which vanilla KLEE couldn't detect. On the next slide, I will explain the detail of our technique. Well, this is an overview of our technique. At a high level, HOMI continuously interact with the symbolic executor until the given time budget expires. At first, HOMI takes as an input the test case generated by symbolic executor, and it updates the probabilistic pruning strategy. Then the executor performs the symbolic execution with this updated strategy, and then update the test cases. Again, HOMI updates the probabilistic strategy based on these accumulated test cases, and we repeat this process during the given time budget. Here I will explain how our first key idea, probabilistic pruning strategy, works. Our pruning strategy decides the set of state to be pruned based on the following two steps: sampling stage and pruning stage. In the sampling stage, we sample the two values from the two learned distribution respectively. I will explain how to learn this distribution later. So in this slide, let's assume that the learned distributions are given. Okay, the first sampled value is a weight vector theta, which is a k-dimensional vector of real numbers. The role of this vector is to score each state, like the figure on the right. The second sampled value is a ratio value used for determining the number of states to be pruned. After sampling these two values, it goes to the next step, the pruning step. First, to score each state, we represent each state as a feature vector. In our work, a feature is the Boolean predicate on state. More concretely, a feature checks whether the state contains a core branch condition or not, such as the symbolic value alpha equals the character dash. For example, let's look at the first state. The first state contains the first and the fourth core branch conditions, but not the second and third ones. So the feature vector of the first state is marked as 1, 0, 0, 1. In this work, we automatically generate these low-level features based on the accumulated data during symbolic executions. Please read our paper on how to automatically generate feature in detail. After transforming each state as a feature vector, we score each state by calculating inner product of the feature vector and the sampled vector theta. Finally, we prune the state with the lowest scores using the sampled ratio R. Suppose that the ratio R is 40%. We cut out 2 states from 5. The next key idea is a learning algorithm that continuously updates the two distributions. To do so, we use the test case generated by symbolic executor. Our learning algorithm consists of 2 steps: collect and update. In the first stage, we calculate the set of branches covered by each test case. Suppose that symbolic executor generated 4 test cases from T1 to T4. After the coverage analysis of each test case, we can generate data D. For example, in data D, the test case T1 covered 3 branches, B1, B2, B4. Likewise, the total number of branches covered by all test cases is 6 from B1 to B6. After generating data D, we collect promising data. In this work, promising data is the smallest subset of D that can cover the total branches in the set D. In this example, using only 2 test cases, T3 and T4, we can cover all 6 branches. Then using this promising data, we update these two distributions. Intuitively, we aim to increase the probabilities of the weight vector and the ratio used to generate the promising test cases. In this case, promising test cases are T3 and T4. For example, suppose that the weight vector and the pruning ratio used for generating T3 and T4 are given as follows. First, let's look at the first values of the two vectors. As you can see, the first value of the vector are all positive values. So we update the distribution so that more positive values are sampled. Likewise, let's see the second values of the vectors. In this case, we update the distribution so that more negative values are sampled. Based on the same principle, we update third one and fourth one. This is the updated distribution for weight vector. Using this updated one, we will sample the new weight vectors. Likewise, we update the pruning ratio so that the promising ratios such as 40 and 60% are more sampled than before. That is, as this loop iterates, the test cases are more accumulated, then HOMI is able to make smarter decisions about how promising each state is and how many states are pruned. From the next slide, we will show the experiment result of HOMI. Okay, let's start with the experiment setup. We implemented our tool HOMI on top of KLEE. And we compare our technique with vanilla KLEE with 9 different search heuristics. As a testing budget, we allocated 5 hours for all the benchmarks. We also used the default memory budget of KLEE, which is 2 GB. And we repeated the experiment 5 times and averaged the result. Finally, we used 9 open source C programs for evaluation. The largest one is about 60,000 lines. Okay, in terms of branch coverage, combining KLEE and HOMI performs much better than vanilla KLEE without HOMI. In this graph, the x-axis denotes the testing period and the y-axis denotes the number of covered branches. And the purple line denotes the result of HOMI. As you can see, HOMI achieves the highest branch coverage on all benchmarks. In terms of the number of candidate states, HOMI is able to maintain a very small number of states compared to vanilla KLEE on all benchmarks during symbolic executions. Finally, in terms of bug finding capability, HOMI is able to find 5 reproducible bugs on 3 benchmarks, GAWK, grep, and combine. And each column shows the benchmark and crash type and the bug trigger input generated by HOMI, and the error location and the success or failure mark. Among the 5 bugs, and these 3 bugs are only detectable by HOMI. Okay, now wrap up this talk. The goal of HOMI is to automatically minimize candidate state while keeping promising state during symbolic executions. To do so, we represent 2 key ideas, a probabilistic state pruning strategy and learning algorithms. In experiment, HOMI greatly enhances the performance of a symbolic executor by minimizing the number of candidate states, by increasing the number of covered branches, and by finding more rare bugs in open source C programs. Lastly, as I mentioned before, you can enjoy our state gardening tool HOMI by downloading this GitHub URL. And please don't forget to mark the star on our GitHub. This is the end of my talk. Thank you for listening.